Hello, my name is José Martín-García. I'm manager of the special projects team in the research and development department. Today, Jeff and I will be presenting recent progress in the Wolfram Astronomy functionality. So this is the outline of the talk. First, I will present two new functions, AstroRiseSet and FindAstroEvent, and then Jeff will present additional functionality in the second part of the talk. So in 14.1, earlier this year, we introduced AstroRiseSet. So the syntax is very easy. So we want to find out when a given object rises or sets or other events from a given location on a given date. And it has this simpler syntaxes. So to set the nomenclature, so recall that as the Earth rotates or any other body from which you may be observing, an object like this one rises on the east in the northern hemisphere, then it reaches an upper altitude, what we call the upper culmination, and then it sets on the west. And of course, on the other side, it has a lower culmination. So AstroRiseSet will be able to compute these four events. Let's see examples. First, with the moon. So we compute these things. And so we see that the next rise of the moon will be on this date, later today. The next set will be tomorrow. We can observe from a different location, say Paris. We will get this. And of course, in order to get the right date or time for that location, we have to use the time zone corresponding to Paris. And that's the time in which people in Paris will see the moon rise. You can also say, well, I want to find the first rise after this date, the first year of 2025, and we get that result. Something that we need to describe is what do we mean by rising and setting. And so to do this, we compare. This is the date of moonrise that we just computed. We ask astroposition, where will the moon be at that instant? And so we see that it will have a negative altitude. That's because what we consider the moonrise instant is when the moon on the way up touches on the upper part the horizon. This line is the horizon, right? So that defines the moment of moonrise. We can compute another moment, which is the moment of moonrise, by saying that we want to reference the center of the moon to the horizon. And so we get a moment which is like 2 minutes later. We can do the same thing for the for the upper limb. And so here, and so you see we get even later, 2 more minutes later, right? And so that will be the map. That's the instant of moonrise, considering the lower limb. Now let's do a few examples with the sun. That's the next instance of rise for the sun and the next instance of set for the sun. So we always had these two functions, which of course return now the very same instant. With the sun, we want to consider what is called the moments of twilight, and we have 3 of them as standard. So this is the sunset, considering the center of the sun rather than the upper limb. The civil twilight is defined to be when the sun reaches 6 degrees below the horizon. Then the nautical twilight is even later, so it's darker, 12 degrees. And the astronomical twilight, when astronomers can start making observations with a very dark sky, is even later, 18 degrees below the horizon. If we compare the 3 moments, we see that there is a difference of around 30 minutes between any pair of these, right? So the later it gets, the darker it is. These are moments that are tabulated in almanacs. So you can compute them now with sunset and sunrise. And finally, let's talk about upper culminations. So this is the moment of the next upper culmination that you can consider like the moment of solar noon. This is the moment in which the sun is highest in the sky. And so if we compute the position of the sun at that instant, we see that because we are in the northern hemisphere, the sun is going to be exactly on the south and at this elevation. If we call solar time, we see that solar time knows this is noon from the point of view of the sun. So this is 12 hours modulo some numerical error. But consider the instant at which in civil time we are getting that instant. So it's 38 minutes after that. So this is a matter of our longitude, time zones, daylight savings, everything is mixed up here. But this is the moment in which the sun is highest in the sky. So we can see it in an eclipse map. So that's the moment. So recall that that's the ecliptic, that's the path of the sun in the sky. That's the projection of the Earth equator out. And so we see that's what happens during the day. The sun rises, then it reaches the maximum height, 40 degrees, so 10, 20, 30, 40 degrees, and then it goes down. Notice how it travels parallel to the equator. And it's below the equator because we are after the autumn equinox. Right? So we can also compute lower culmination, which is solar midnight, also 38 minutes after civil midnight. And we can observe from other bodies. For example, let's take this interval from beginning of 2024 to the end of 2024, and we are going to compute when Mars rises and sets as observed from this location of the moon, which is like the center of the disk of the moon, observed from the Earth, more or less. And so during that whole year, it happens multiple times. Now, of course, because the moon rotates slower, you see that the rises and sets are separated like 2 weeks apart. And now, if we try to compute when the Earth rises and sets from that same point, we see that it never does, because of course the Earth from that location is always very high in the sky. The moon is always facing us, at least from this point. If we go to the border, like 88 degrees longitude, now because the moon has a little bit of oscillation called libration, then from those points, the Earth does rise and set. And we get here the date. So you see how it all depends on the dates and the location. Okay, so that's all for AstroRiseSet. You can observe anything from anywhere in the solar system and compute various events at any time. Now, let's look at the new function that will be introduced in 14.2, which is FindAstroEvent. This is a lot more powerful. It can compute many more types of events. So here we have, again, the type of event, the date we are interested in, and the location we are observing from, again, with some shortcuts. Let's look first at equinoxes and solstices. So, for example, that's the next equinox, which is going to have, solstice, which is going to happen in December. That's the winter solstice, precise to second. This is the something that you will find tabulated in many places. That's the March equinox, also called vernal equinox or spring equinox in the northern hemisphere, not in the southern hemisphere. The June solstice and the September equinox. So in order to understand what this means, we can compute this map. And here we see again the path of the sun during the year and the celestial equator, the Earth equator projected outwards. Now, this has months. So for example, here we're starting March. We are March 21. That's April, etc. Right? That's because the sun moves along this line during the year. So I'm now advancing months. Now at that moment here, it will get up the highest point. That will be the summer solstice. Then it will go down. It crosses the equator again. That's the autumn equinox. And then it goes down again. You see how it's crossing all these constellations of the zodiac. Here it reaches the highest point, the lowest point, that's the winter solstice, and then it goes up again to the equinox, the March equinox of 2026. We can compute all the equinoxes and solstices of during the decade, and here we can put them nicely in a tabular object. Okay, so now other types of events that we can compute are called conjunctions, oppositions, and quadratures. So if we are observing from Earth, and we are observing, for example, a planet going in this orbit, an outer planet, then that's called the opposition. You see it's opposed to the sun. That will be the conjunction. So it's just behind the sign, and these are the quadratures. If we are looking at an inner planet, like I don't know, Venus, then we will have the inferior conjunction, the superior conjunction. There is never an opposition, and then we never have quadratures, but we have the greatest elongation in the east or in the west. Right? So these are the 4 here and 4 here events we are interested in. For example, that will be the next conjunction with Jupiter. That will be the next opposition, western quadrature, and eastern quadrature. Right? The inferior conjunction of the Earth as seen from Saturn. Again, we can observe from anywhere in the solar system. And so that meant when the Earth passed in between the Sun and Jupiter, which was an event observed by the Huygens probe. There are very beautiful videos in YouTube showing this event, right? And it shows how the Earth takes 12 hours to cross in front of the Sun as seen from Jupiter, right? In spite of how fast the Earth moves, it takes 12 hours.
Saturn, actually.
Saturn, yes.
Yes.
Sorry. Okay, and then I just want to present 2 more types of events. Distance events, for example, when do we have the periapsis of Mercury, or in other words, the perihelion of Mercury, or the perihelion of the Earth, perigee of the Moon. We can see when Callisto gets closer to Jupiter, that's called the perigee, etc. And we have the same apoapsis and aphelion, etc. events. Finally, angular separation events. Rather than computing distances, we can compute minimum of separation. That's called an appulse. And here we can find the local minimum of Jupiter and Saturn between 2010 and 2035, and we get all these dates. We can plot them in a plot. That's our function to compute separation, and we see how those dates correspond to all the minima in this curve. The absolute one happened on this date, and they were so very close that looking at them through a telescope allowed you to see simultaneously the moons of Saturn here and the moons of Jupiter here. They were really close, like 0.1 degrees. Okay, and that ends my part of the talk. So now we'll stop sharing and I will let Jeff continue. Thank you.
So I'm Jeff Bryant. I work in the Wolfram Alpha team. So I mainly work on the kind of the data side of thing and some Wolfram function repositories, kind of ancillary data on top of some of the other stuff that Jose works on, where he works more on the core stuff. And a few things that I just wanted to highlight on top of the new core stuff coming into Mathematica itself is that we have a new entity type coming. We're going to have black hole data. So with black holes, for quite some time, we've had, at least on alpha, we've had support for theoretical constructs. So a theoretical black hole with a known mass. So here you can see, for example, this is a Wolfram function repository item called black hole model data. It's for a Kerr-Newman black hole. You want to know the temperature of that black hole, and it has a known mass of 10 solar masses. Here you can see the angular momentum and the charge. So here we've got a chargeless black hole. And you can see here the temperature. So very, very cold. So this is a theoretical construct. You could do things like this, but in modern day, we actually know where black holes are. So now we can actually essentially point to them in the sky and say, hey, there's a black hole, and we can measure the properties. And we wanted to have a collection that represented that known data. And so with the new entity type, we have, as with most of the other astronomical entity types, quite a few properties. I leave it to the user just for a matter of time here that I'm not going to read all of these, but most of it's positional. It tells you what constellation it's in, but it includes properties like mass, temperature, Schwarzschild radius, surface gravity, all these kinds of things. So you can explore that. You can actually, let's see here. Give me just a second here. My system's trying to render here. Here's a star chart where I've plotted all the black holes that we currently have. I expect that with time, this data set will continue to grow as we curate more and more black holes that are known. But you can see that they're scattered all along the sky. They're not just constrained to within the Milky Way. Some of them are in galaxies that are much further away. So they're way up here in the halo and beyond. So kind of irregularly distributed all over the sky. Here's an example where you can query for black holes that are, well, in this case, it's the nearest black hole. So in this case, it's a star system, and it's in the star system of V Puppis. Interesting thing to note about black holes, they don't really have names. They're typically named after either the star system they're found in or the galaxy that they're found in. They don't have a name themselves. So in this case, it's the black hole within the V Puppis star system. So here you can see where I've queried entity value for the V Puppis, and I've said, give me all the system members and give me their masses and convert those into solar masses. And here you can see that it has a star that's 14 solar masses, one that's 7.3 solar masses, and it has one here, a black hole that's 10 solar masses. So this is actually a triple system, but one of those components is a black hole. Okay. Something else that I wanted to add on here, this is not built into the system, but it's something you can already use, and it's been actually quite useful here in the recent history. We've had a lot of solar activity going on. And so since July of last year, we've had a lot of use of a new Wolfram function repository item called SolarImage. This actually ties into the HelioViewer project, which provides an API for very recent NASA and European Space Agency solar imagery. And you can actually feed in a date or a different instrument, and you can get either visual images like this one. So here you can see a visible light image of the sun currently. Actually, if I reevaluate this, let's give it just a second here. And there's the current image of the sun. So you can see where the sunspots are. You can also feed in a different date. So here's what the sun looked like on a particular date. So this was on October 9th, 2024. Here's where I've switched instruments. Notice that I put a 9 here. We have quite a few instruments. Names are not intuitive, so it wouldn't really be useful to have a string here. So it's easier just to represent them with a number, and then we have an association you can query for to find out what number corresponds to which instrument. In this case, we're looking at a far ultraviolet. You can see here a solar flare going off in the middle of this particular date object, and you can see that in the extreme ultraviolet. You can also query for a range of dates, and you can get a series of images, and that's returned as an event series. Now, the thing I should note is that this particular API returns images that are quite large. They're actually 4K in size. And if you're getting a lot of these, it can be, you have to wait, you might have to wait a couple minutes if you're going to get, say, 100 images or so. But if you're patient, you'll eventually get back an event series, and then you can do all your image processing locally. But that's what SolarImage does. It will return an event series, which then leaves you to then pull it apart and reassemble it as a video, whatever you want to do. Given that that step is a little bit tedious, the next thing that I introduced was a follow-up Wolfram function repository item called SolarVideo. This just takes that extra work out. So here, once again, we're provided another date range. And I've called SolarVideo. You feed in that date range, and once again, you ask for that same instrument 9. And what you get back is, this is specifically not done with very many frames, but you can see the video going. It actually looks much more impressive when you actually have a lot more frames in it, but for brevity, I just included a few frames here. But so yeah, so this is very useful. You can combine that with an older Wolfram function repository item we have called space weather data that allows you to get actually X-ray measurements from the sun, solar sunspot counts, solar wind measurements, temperature, all that kind of stuff is in space weather data. We've had that for quite a while. So We've had quite a few auroras recently as a result of this solar activity. So these are some nice tools that are nice to help you predict when something might happen. Something I did want to add is something else that's in the news right now is we have a comet that's in the sky right now. So here's kind of some homework for you. You should be able to go out after the sunset this evening. And you should be able to see this comet. It is naked eye. However, it's just above naked eye visibility. It's not going to be blaringly obvious. You have to know where to look. So it's going to be kind of due west, about 45 degrees up or so, and you'll need to look for it. And the other complication is right now the moon is nearly full, which means the sky doesn't get super dark right now. By the weekend, things should be a little bit nicer, and this comet should be visible, I don't know, for the next month or so. It'll get slightly fainter each day, but it'll also get a little higher. So be on the lookout. There's some code in here for how to compute this. So here is the star chart. So this is showing looking west. This is from Champaign, which is my view, looking west at civil twilight, evening civil twilight. And this shows you where the comet will be tonight. So you can see it's almost due west. It's in the constellation of Serpens. There aren't any really particularly bright stars here, but the one thing you can see is Venus is down here in the lower right. So if you find Venus, that's going to be very easy to see in the night sky. There's also a bright star called Arcturus that'll be over here in the northwest. So in the southwest, you'll have Venus, and the northwest, you'll have Arcturus, and in between and above, you'll have the comet. So that's the area of the sky you want to look at. And if you have binoculars, that'll help things. Or if you have a camera, cameras can see it much easier. So that's your homework for tonight. Go observe a comet. You can use Wolfram Language to generate a finding chart for you.